Limits involving more trigonometric functions. Aside from the sine trigonometric limit that we talked about earlier, there are more that we're going to be discussing. The second one to know is that the limit of the quantity cosine x minus 1 divided by x as x approaches 0 is equal to 0. Let's use some trigonometric identities to rewrite the function and to prove that this limit is indeed valid. We'll start by multiplying both the top and bottom by the conjugate of the numerator, which is cosine of x plus 1. When we do that, we will get cosine squared of x minus 1, and then in the denominator, we will get x times the cosine of x plus 1. And due to the Pythagorean identity of sine squared x plus cosine squared x being equal to 1, we can subtract cosine squared x to both sides, and we would get that sine squared x is equal to 1 minus cosine squared x. And then if we multiply both sides by -1, we get that the negative sine squared of x is equal to -1 plus cosine squared x, or cosine squared x minus 1. So therefore we can take negative sine squared x and substitute it into the numerator. From there we can split up the negative sine squared x into sine of x over x and negative sine of x over cosine of x plus 1. Now we can use substitution and the fact that the limit of sine of x divided by x as x approaches 0 is equal to 1 to find this limit. So we can rewrite the first term, or the first factor in our product expression, as the limit of sine of x divided by x as x approaches 0 times the limit of negative sine of x divided by the quantity cosine of x plus 1 as x approaches 0. We know that the first one, this first limit, is equal to 1, so we can put that in there, and then we can actually take this limit. If we substitute 0 in for x and negative sine, we get 0, and in the denominator, cosine of 0 is 1, and 1 plus 1 is 2. So 0 over 2 is equal to 0. So then we have 1 times 0, which is equal to 0. So this proves that the limit of the quantity cosine of x minus 1 divided by x is equal to 0. Evaluate the limit of cosine of r minus 1 divided by r squared as r approaches 0. Similar to the last example, the first step here is going to be multiplying both the numerator and denominator by the conjugate of the numerator in order to get a Pythagorean identity in the top. And multiplying by cosine of r plus 1 over cosine of r plus 1 gives us the cosine of r squared minus cosine of r plus cosine of r minus cosine of r, which cancel out, and then minus 1. And then in the denominator, we'll get r squared times the quantity of cosine of r plus 1. And then again, based on the Pythagorean identity of sine squared plus cosine squared being equal to 1, we can substitute negative sine squared of r in for cosine squared of r minus 1. Next, we can split up this numerator into two factors, sine squared of r times -1. And then we can split up the two factors in the denominator to be r squared times, in the first fraction times cosine of r plus 1 in the second fraction. Now we can use direct substitution to finish simplifying and then evaluating our limit. So we had two separate fractions being multiplied, and we're taking the limit of that product. Well, one of the properties that we have is when you have a limit of a product, you can write it out as the limit of each factor and still multiply the two together. So we have the limit of sine squared of r divided by r squared as r approaches 0 times the limit of -1 divided by the quantity cosine of r plus 1 as r approaches 0. And then from there, we can substitute 1 in place of the first limit. Now, why can we do that? Well, we can do that because the limit of sine of r over r as r approaches 0 is equal to 1. Well, sine squared of r over r squared is equivalent to sine of r divided by r quantity squared. So we would basically have 1 squared, which is still equal to 1. So that's why we can take this 1 value and substitute it in for this expression to get this one right here. 1 times the limit of -1 divided by the quantity of cosine of r plus 1. And then from here, we can substitute 0 in for r. And when we do that, the cosine of 0 is 1, and 1 plus 1 is 2. So we get a 2 in the denominator, and we still have a -1 in the numerator. So we have 1 times -1/2, which is -1/2. Evaluate the limit. The limit of 4x divided by cosine of 4x as x approaches 0. Now this function that we're trying to take the limit of doesn't really resemble any of the limits that we have fully defined. So let's actually see if direct substitution works here. So we have 4 times 0 over the cosine of 4 times 0. Well, that'll be 0. And then if we evaluate the angle here, we have 4 times 0, which is 0, and the cosine of 0 is 1. So we can actually evaluate it to get a final answer of 0. The third trigonometric limit to know is the limit of tangent of a times x divided by a times x as x approaches 0 is equal to 1. And we can prove this by showing that the limit of tangent of x divided by x as x approaches 0 is equal to 1. First, let's rewrite the tangent of x as sine of x divided by cosine of x. This will now make our limit be the limit of sine of x divided by cosine of x, all divided by x as x approaches 0. This can also be rewritten as the limit of the quantity sine of x divided by cosine of x times 1 over x as x approaches 0. Now we can switch the numerators to make the evaluating this limit work better for us. It'll go from the limit of the quantity sine of x divided by cosine of x times 1 over x as x approaches 0 to this one, the limit of the quantity sine of x divided by x times 1 over cosine of x. So then we can evaluate and use substitution using from limits that we know. So we have the limit of 1 divided by cosine of x as x approaches 0. If we substitute 0 in for x to evaluate it, cosine of 0 is 1, and 1 over 1 is 1. So that's how we get this value. And now, this other one, the limit of sine of x divided by x as x approaches 0 is also equal to 1, and we've proven that. And then 1 times 1 is equal to 1. The last limit to know is not a trigonometric limit. However, it will be used as the foundation for a new definition of the number e in the next unit. Do you remember e? Let's try to graph f of x is equal to the quantity 1 plus x raised to the 1 divided by x power. Pay close attention to the value y is approaching as x is approaching 0. Notice from the left, it's approaching a number between 2 and 3. And similarly, as we approach 0 from the right, it's approaching that same value. Despite having that undefined y-intercept, because if we substitute 0 in for x here, we would get 1 plus 0 raised to the 1 over 0 power. So we would get 1 raised to the 1 divided by 0 power, which we can't actually do. So that's why we're looking at the graph to see this limit, since it's undefined at 0, or the y-intercept. Despite that fact of being undefined at the y-intercept or when x is 0, the value is approaching to approximately 2 and 718 thousandths, which is e. And that allows us to define the limit of 1 plus x raised to the 1 over x power as x approaches 0 to be e.